So the James Webb Space Telescope is, by most measures, the most powerful telescope that humanity has ever built. It sits a million miles from Earth at the second Lagrange point, staring into the infrared universe with a 6.5 meter wide mirror made of gold-plated beryllium. Trump would love it. It cost around $10 billion, it took decades to design and build, and it has already transformed our understanding of everything from the earliest galaxies to the atmosphere of distant exoplanets. But here's the thing. Right now, over in the Atacama Desert of northern Chile, engineers are constructing a telescope that will, in key ways, outperform JWST. This is the Giant Magellan Telescope, and when it's finished, sometime in the early 2030s, it will have roughly 10 times the resolving power of the Hubble Space Telescope and around 4 times the spatial resolution of James Webb itself at certain wavelengths. Its primary mirror spans 25.4 meters. That's about 368 square meters of light collecting surface, roughly the area of a basketball court, made entirely of glass, except it's not one mirror, it's 7. That is 7 of the largest telescope mirrors ever manufactured, each one 8.4 meters in diameter, arranged in a flower petal pattern and polished to a smoothness measured in nanometers. The whole thing sits inside a rotating enclosure about 65 meters tall, perched on a mountaintop that engineers literally blasted flat to make room for it. The telescope mount alone weighs 2,100 tons. The project has cost around $2.5 billion with funding from institutions across 7 countries. And those mirrors, each one takes 4 years to make in a laboratory that's hidden beneath a football stadium in Arizona. For real. This is one of the most ambitious scientific instruments ever attempted. It's designed to detect biosignatures in the atmospheres of Earth-like exoplanets, to resolve the earliest structures of the universe, and to answer questions that even James Webb can't touch. The idea. Since Galileo first pointed a crude spyglass at the moon in 1609, the history of astronomy has followed a pretty consistent pattern. You build a bigger telescope, you see things nobody expected, revolutionize our understanding of the universe, and then you start planning an even bigger telescope. The world's largest telescope has roughly doubled its aperture every 40 to 50 years, and each generation has uncovered phenomenon that the previous generation couldn't have imagined, from the moons of Jupiter to the expansion of the universe itself. Quite impressive, isn't it? But by the late 20th century, ground-based astronomers were starting to hit a bit of a wall. The problem was the atmosphere. Earth's turbulent air bends and distorts incoming starlight, which is why stars twinkle when you look at them from your backyard. The more you know. That twinkling might be pretty, but for astronomers trying to resolve fine details in distant galaxies or separate the faint glow of an exoplanet from its parent star, it's kind of a pain in the arse. No matter how large your mirror, atmospheric turbulence limits what you can see. And that is, of course, why space telescopes became a thing. Hubble, launched in 1990, sits above the atmosphere entirely, which means no twinkling, no distortion, and images sharp enough to transform cosmology. James Webb pushed even further, moving 1 million miles from Earth to observe in infrared without interference from our planet's heat or air. The message seemed pretty clear. If you want the best views of the universe, you've got to leave the ground behind. But here's the thing. Space telescopes are ridiculously expensive. They are incredibly difficult to repair. It's 1 million miles away. And once you've launched them, you're stuck with whatever instruments you put on board. Ground-based telescopes, by contrast, can be upgraded, maintained, and expanded over decades. And in the 1990s and 2000s, a new technology started to change the calculus entirely, and that was called adaptive optics. These are systems that could measure atmospheric distortion in real time and actually correct for it, flexing the telescope mirrors thousands of times a second to undo the damage that the air was causing to the measurements. Suddenly, ground-based telescopes could achieve something close to the sharpness of space-based ones while still benefiting from mirrors far larger than anything you could realistically launch into orbit. This realization sparked a global race to build what astronomers now call, creatively, extremely large telescopes, or ELTs. They really did hit the nail on the head with that name, didn't they? Europe began planning the also Really? Aptly named telescope, extremely large telescope? A 39-meter monster under construction in the Atacama Desert, a consortium of American, Canadian, Indian, and Japanese institutions started work on the 30-meter telescope, plans for Mauna Kea in Hawaii, and a separate group of American and international partners launched the Giant Magellan Telescope project, also destined for Chile, with a unique 7-mirror design that promises exceptional resolution and light-gathering power. Now, these 3 projects, not exactly competitors in the traditional sense, they are designed to observe different parts of the sky and answer different and complementary questions, but they are racing toward first light. And for American astronomers in particular, there's a bit of an urgency here. The 2020 Astronomy and Astrophysics Decadal Survey, which sets priorities for US research funding, ranked the development of an extremely large telescope as absolutely essential for maintaining American leadership in ground-based astronomy. The survey recommended that the National Science Foundation support both GMT and TMT as a part of a unified US extremely large telescope program, warning that without direct access to ELT-class facilities, American astronomers risked falling behind their European and Asian counterparts within only a decade. At the center of all of this sits the Giant Magellan Telescope, a $2.5 billion gamble that you can build something on the ground that outperforms the most sophisticated observatory ever launched into space. Why build this thing? So, the scientific case for building something like the Giant Magellan Telescope comes down to a handful of questions that smaller instruments simply can't answer. And those questions are, frankly, some of the biggest questions that humans have ever asked. First, and most compelling, are we alone? In the last 3 decades, astronomers have discovered thousands of exoplanets orbiting other stars, including dozens of rocky worlds in the so-called habitable zone where liquid water could theoretically exist. But discovering a planet and actually characterizing it are 2 very different things. To determine whether a distant Earth-like world has an atmosphere, whether that atmosphere contains water vapor or oxygen or methane, whether it shows the chemical fingerprints that might indicate life, you need a telescope with extraordinary resolution and light-gathering power. You need to separate the very faint glow of a small planet from the overwhelming glare of its parent star, and then you need to spread that tiny trickle of photons into a spectrum detailed enough to reveal individual molecules. Science is insane. Current instruments can do this for large, hot gas giants. Doing it for something the size of Earth orbiting a sun-like star, that requires a mirror 20 meters across or more. Second, this is the question of cosmic origins. James Webb has already started finding galaxies that formed astonishingly early in the universe's history, some of them appearing as surprisingly bright little red dots in deep field images. But Webb's observations raise as many questions as they answer. How did these galaxies form so quickly? What were the first stars actually like? How did the chemical elements we're made of get scattered through the cosmos? Following up on these discoveries requires the kind of detailed spectroscopy that only a ground-based giant can provide, breaking the light from those ancient galaxies into fine enough slices to measure the velocities and chemical compositions of their stars and gas. And then there's the dark universe. We know that ordinary matter, the stuff that makes up stars and planets and us, accounts for only about 5% of the total mass energy of the universe. The rest is dark matter and dark energies, invisible forces that shape the structure of the universe on the largest scales. Mapping the distribution of dark matter, understanding how it clumps around galaxies, testing whether our theories of gravity hold up in these extreme environments, it all demands precision measurements of millions of objects across vast stretches of sky. The kind of measurements that require both enormous light collecting areas and sophisticated multi-object spectrographs capable of observing hundreds of targets all at the same time. These questions drove a generation of astronomers to start thinking seriously about extremely large telescopes in the 90s and early 2000s. One of the key figures was Roger Angel, an astronomer and optical scientist at the University of Arizona who had pioneered new techniques for casting large telescope mirrors using a spinning furnace and a honeycomb structure that dramatically reduced weight while maintaining rigidity. Angel's work at what would eventually become the Richard F. Karras Mirror Lab made it possible to manufacture mirrors far larger than traditional methods allowed, and his innovations became the foundation for the Giant Magellan Telescope's unique design. By the mid-2000s, a consortium of research institutions had begun formalizing plans for GMT, with the Carnegie Institution for Science, Harvard University, the Smithsonian Institution, MIT, and several international partners signing on to fund and build what they hoped would become one of the most powerful observatories on Earth. Rebecca Bernstein, who now serves as GMT's chief scientist, has described the project's core mission in strikingly direct terms. It's to find other Earths and determine whether any of them might harbor life. No big deal there. The perfect mountain, Las Campañas. Okay, so if you are going to build one of the most sensitive optical instruments on Earth, you need to put it somewhere with almost no atmosphere in the way. And for astronomers, that means going high and going dry. The Giant Magellan Telescope is constructed at Las Campanas Observatory in Chile's Atacama Desert, roughly 2,516 meters above sea level and about 100 kilometers inland from the Pacific coast. The Atacama is one of the driest places on the planet, so arid that parts of it are regularly used as stand-ins for Mars in scientific studies and also in films. More importantly for astronomers, the air above Las Campanas is exceptionally stable and contains very little water vapor, which means sharper images and better sensitivity to infrared light. The observatory enjoys clear skies more than 300 nights a year, with some of the best seeing conditions, the technical term for atmospheric steadiness, of any major telescope site in the world. Location matters for another reason too. From this latitude, in the southern hemisphere, GMT will have direct views of some of the most scientifically valuable targets in the sky. This includes the center of our own Milky Way galaxy, the large and small Magellanic Clouds, which are the nearest satellite galaxies to our own, and Proxima Centauri, the closest star to the Sun and host to at least one potentially habitable exoplanet. Northern Hemisphere telescopes simply cannot observe these objects as well, if at all, which gives GMT a significant advantage for certain kinds of science. The Carnegie Institution for Science has operated telescopes at Las Campañas since the 1960s, so the infrastructure and institutional knowledge were already in place when the GMT project began. But the existing summit wasn't quite right. In 2012, engineers detonated explosives to blast the peak flat, removing the top of the mountain to create a level platform large enough to accommodate the telescope and its enormous rotating enclosure. Of course, the Atacama's advantages come with challenges. The site experiences dramatic temperature swings between day and night, strong winds that can gust to dangerous speeds, and the ever-present risk of earthquakes in this seismically active region. All of which means the telescope's mountain enclosure need to be engineered to survive conditions that would destroy a more delicate structure. An engineering marvel. Alright, now let's talk about the heart of this telescope, the mirrors themselves. The Giant Magellan Telescope uses 7 primary mirror segments, each one 8.4 meters in diameter, arranged in a pattern that looks a bit like a flower with 6 petals surrounding a central disc. Lovely. Together they create an effective aperture of 25.4 meters and a total light collecting area of 368 square meters. Here's what makes this design particularly challenging. The central mirror is symmetric, shaped like a normal telescope mirror, but the 6 outer segments are what's called off-axis. They're essentially slices of a much larger imaginary mirror, which means each one has an asymmetric curve that is fiendishly difficult to manufacture and test. You can't just spin one up and assume it's right because there's no simple axis of symmetry to check against. Every single one of those outer mirrors is a unique optical surface that has to be ground and polished to a specific, non-intuitive shape with nanometer level precision. So, where'd you build something like that? Well, under a football pitch, we talked about that already. The Richard F. Karras Mirror Lab sits underneath the east stands of Arizona Stadium at the University of Arizona in Tucson, and it is one of the only facilities on Earth capable of producing mirrors this large. The process starts with about 20 tons of E6 borosilicate glass, a low-expansion material manufactured by Japan's Ahara Corporation that can withstand extreme temperature changes without warping. That glass gets loaded into a rotating furnace and heated to around 1,100 165 degrees Celsius until it melts and flows into a mold. The furnace spins while the glass is molten, and centrifugal force pushes the material outward and upward against the edges, naturally forming a shallow curved shape that approximates the final parabolic surface. This technique, called spin casting, saves enormous amounts of grinding later because the mirror comes out of the oven already close to the right shape. The mold itself contains a honeycomb pattern of ceramic cores. That's another innovation pioneered by Roger Angel and his team. When the glass solidifies around these cores, and they're eventually removed, what's left is a mirror with a hollow, honeycomb structure inside rather than a solid slab. This cuts the weight massively. Each finished segment weighs around 16 to 18 tons instead of the roughly 50 tons that a solid disc would weigh, while maintaining the rigidity needed to hold an optical surface steady. After casting, the mirror cools for about 6 months. Rushing this process would introduce internal stresses that would make the glass impossible to polish accurately. And once cooled, each segment moves into a grinding and polishing phase that takes roughly 3 to 4 years, during which technicians gradually shape the surface to the required precision. The final smoothness is pretty absurd here. The peaks and valleys on the finished mirror surface are smaller than 25 nanometers, and that might not mean much to you, but how about this? It's less than 1,000th the width of a human hair, and if you scaled one of these mirrors up to the size of North America, the tallest bump would be about 3 centimeters high. The first GMT mirror was cast in 2005 and completed in 2012. Subsequent segments were cast in 2013, 2015, 2017, 2021, and the 7th and final mirror entered the furnace in 2023. It's a long sentence, deep breath. Each one represents years of work at about $30 million in value, each one, which means the stakes during handling and transport, they're rather high. When the first completed mirror was shipped to Chile, it traveled by truck to the port of Houston, then by sea around the tip of South America to the Chilean coast, and finally by road up into the mountains. The entire journey required custom transport frames designed to absorb shocks and vibrations, and teams monitored sensors on the crate throughout the voyage. Damaging even one segment would set the project back years. But even with all 7 primary mirrors in place, GMT still faces the fundamental problem of atmospheric turbulence, and solving that requires another set of mirrors entirely, ones that can reshape themselves 2,000 times every second. This whole project is insane. I just want to say, it's just incredible what we can do. Adaptive optics and secondary mirrors. Okay, so starlight travels across billions of kilometers of empty space in perfectly straight lines, undisturbed and pristine, and then in the last 100 kilometers before it reaches your mirror, it passes through the atmosphere, which ruins everything. Pockets of warm and cool air constantly rise and fall, each with slightly different densities that bend light in slightly different directions. By the time that starlight hits your carefully polished mirror, it's been scrambled into a shimmering, shifting blur. Not great. This is where those adaptive optics that we mentioned earlier come in, and it's genuinely one of the cleverest pieces of engineering on the entire telescope. GMT uses 7 secondary mirror segments, each about 1.1 meters across, mounted above the primary mirrors in a structure called the secondary mirror assembly. Each one is a razor-thin shell of glass, just 2 millimeters thick, bonded to the front of a reference body containing nearly 5,000 tiny actuators. These actuators are essentially voice coils, but same basic technology that moves the cone in a loudspeaker, and they can push and pull on the glass shell to reshape its surface with extreme precision. The system measures incoming starlight using sensors that detect how the wavefront has been distorted by the atmosphere, calculates the corrections needed to undo that distortion, and then commands the actuators to flex the secondary mirrors into exactly the right shape to compensate, doing that 2,000 times a second. The telescope can run its adaptive optics in several different modes depending on what astronomers need. Ground layer adaptive optics corrects for turbulence close to the ground and sharpens images across a relatively wide field of view. Narrow guide star mode uses a bright star near the target as a reference, achieving extremely high quality corrections, but only for a tiny patch of the sky. And laser tomography mode fires powerful laser beams into the upper atmosphere to create artificial guide stars, allowing good corrections even when there's no convenient bright star nearby. And again, this is all just insane insanely cool. Each mode has trade-offs, but together they give GMT flexibility to tackle a huge range of science. The payoff for all of this complexity is fucking incredible resolution. With adaptive optics running, GMT is designed to achieve what's called diffraction-limited imaging, meaning the sharpness of the image is set by the physics of light waves rather than the atmospheric blurring. At the near-infrared wavelengths, that works out to about 0.01 arcseconds. That's roughly 10 times sharper than Hubble and around 4 times sharper than James Webb at comparable wavelengths. For a ground-based telescope, that is insane. And it's what makes GMT capable of science that even a space telescope can't match. The moving mountain. Okay then, you've got 7 mirrors weighing about 17 tons each and costing $30 million, a set of ultra-thin adaptive secondary mirrors that flex thousands of times per second, and a whole suite of instruments that are needed to capture photons with exquisite precision. So, how do you hold all that together while pointing it at different parts of the sky throughout the night, smoothly tracking objects as the Earth rotates and doing it all without introducing vibrations that would blur your images and ruin everything? Well, the answer is one of the largest and most precisely engineered telescope mounts ever built. GMT's mount stands about 39 meters tall and sits on a concrete pier 22 meters in diameter anchored deep in the level mountaintop. The structure weighs about 1,800 tons bare, and closer to 2,100 tons once you add the mirrors, instruments, and support equipment. Moving something that heavy with the smoothness needed for astronomical tracking sounds almost impossible, but the mount accomplishes it through a series of hydrostatic bearings that essentially float the entire structure on a thin film of pressurized oil. The oil film eliminates metal-to-metal contact, which means no stick-slip friction, no juddering, just smooth, continuous motion as the telescope swoops across the sky. The enclosure that surrounds all this is equally impressive. Standing about 65 meters tall and roughly 60 meters across, it's the largest enclosure ever built for a Gregorian telescope, the design type that GMT uses. The whole structure rotates in sync with the mount, completing a full 360-degree turn in about 4 minutes and features enormous retractable doors that open to expose the mirrors to the sky. The enclosure is actually also an active part of the optical system. Engineers have designed it to minimize internal air turbulence by carefully controlling temperatures and airflow, ensuring that the atmosphere inside the dome matches the cold night air outside as closely as possible. Each primary mirror segment sits in its own supported cell, a steel structure containing 165 actuators that actively maintain the mirror's precise shape as the telescope tilts to different angles throughout the night. Without these supports, gravity would distort the glass as it moved, ruining the careful figuring that took years to achieve. The telescope also has protective covers for each mirror that can retract in a little over 2 minutes when observations begin, shielding those $30 million surfaces, the many of them, from dust and debris when not in use. And here's where things get a little bit unusual. Because GMT is still under construction, engineers needed a way to test procedures, rehearse maintenance tasks, and identify design problems before any of the real hardware arrived on site. And their solution was Bob, the builder of observatory behavior. And this is a full-scale digital twin of the entire observatory built using the Unreal Engine gaming platform, and it's accurate down to the centimeter. Engineers can walk virtual avatars through the facility, drive simulated trucks and cranes, practice removing mirrors for recoating, and generally run through any complex operation in a consequence-free environment. One journalist visiting the project described accidentally driving a virtual truck off of a ledge inside the enclosure, which is exactly the kind of mistake that you want to make in a simulation, rather than with real personnel and an enormously expensive mirror. The instruments. Now, a telescope mirror, no matter how large or precisely polished, doesn't actually do science by itself. It just collects light. The actual discoveries happen in the instruments mounted at the focal point, where that gathered light gets split apart, measured, analyzed, and converted into data that astronomers can interpret. And GMT is designed to host some of the most sophisticated instruments ever built for ground-based astronomy. The telescope's Gregorian optical design creates a focal station where up to 10 different instruments can be mounted, either receiving light directly or fed through a clever robotic fiber positioning system called manifest. For first light and the initial years of operation, GMT will carry 4 primary instruments, 2 optimized for visible wavelengths and 1 for the near-infrared wavelengths, each designed to tackle specific scientific questions that no existing telescope can answer. Let's start with the one that might detect life on another world. GCLEF, which stands for GMT Consortium Large Earth Finder, is a high-resolution optical spectrograph designed to measure the Doppler shifts in starlight caused by orbiting planets tugging on their host stars. This is precision down to tens of centimeters per second, sensitive enough to detect the gravitational wobble caused by an Earth-mass planet in a habitable zone orbiting around a sun-like star. But GCLEF can do more than just find planets. It can characterize their atmospheres. You see, when a planet transits in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere on its way to us, picking up absorption signatures from whatever molecules are present. GCLEF is designed to dissect that light with enough resolution to identify oxygen, water vapor, methane, and carbon dioxide, exactly the combination of gases that might indicate biological activity. If there's a living world within a few dozen light years of Earth, GCLEF is one of the instruments that is most likely to find the first evidence. GMAX, the GMT Multi-Object Astronomical and Cosmological Spectrograph, is a mouthful that takes a completely different approach. Instead of staring at one star with extreme precision, it spreads its attention across hundreds of targets simultaneously, capturing spectra from galaxies scattered across a field of view several arc-minutes wide. This makes it ideal for survey work, mapping the large-scale structure of the universe, measuring the redshifts of distant galaxies to trace how matter clumps together over cosmic time, and probing the nature of dark energy by studying how the expansion of the universe has changed across billions of years. Where GCLEF is a sniper rifle, GMAX is a wide-angle lens. For infrared work, GMT will deploy GMT-IFS and GMT-NIRS. GMT-IFS is an integral field spectrograph fed by the adaptive optics system designed to deliver diffraction-limited imaging and spectroscopy in the near-infrared bands. Integral field means it captures the spectrum at every point across a 2-dimensional patch of sky simultaneously, allowing astronomers to build up detailed maps of velocity and chemical composition in a single observation. This is perfect for studying the chaotic environments around supermassive black holes, resolving individual stars in the crowded cores of nearby galaxies, or dissecting the structure of protoplanetary disks where new solar systems are forming. GMT-NIRS, meanwhile, pushes further into the infrared, covering wavelengths from about 1 to 5 microns with high spectral resolution, optimized for cool objects like brown dwarfs, red dwarf stars, and the atmospheres of giant exoplanets. And then there's Manifest, which actually isn't really an instrument at all, but rather an enabling technology that makes the other instruments just a bit more powerful. Picture hundreds of tiny robotic positioners arrayed across the telescope's 20 arc-minute field of view, each one capable of precisely aiming a fiber optic cable at a specific target, like an army of drinking straws scattered across the sky, each one sipping photons from a different star or galaxy and funneling them down to the spectrographs below. And all of that is fantastically interesting, but what it does is it lets GMT observe massive numbers of targets in parallel, dramatically increasing the telescope's efficiency for survey science. A lot of words right there. What's this all mean in practice? Consider a scenario that might play out within GMT's first few years of operation. The Test Space Telescope has already identified a rocky planet orbiting in the habitable zone of a nearby sun-like star, and James Webb has detected hints of an atmosphere during a transit observation. GMT trains GCLEF on that star for dozens of nights, building up enough signal to dissect the atmosphere spectrum in detail. The data shows absorption lines from water vapor, which isn't surprising, carbon dioxide, again expected, but also oxygen and methane together in concentrations that are difficult to explain through purely geological processes. That result definitely wouldn't prove that life exists there, but it strongly indicates it could be possible. Or imagine GMAC surveying thousands of faint dwarf galaxies orbiting the Milky Way, measuring the velocities of individual stars to map out how dark matter is distributed in their halos. These tiny galaxies are some of the most dark matter-dominated objects in the universe, and the precise shape of their dark matter profiles could help distinguish between competing theories about what dark matter actually is. Or GMT-IFs watching stars whip around Sagittarius A star, the supermassive black hole at the center of our galaxy, tracking their orbits with enough precision to test whether Einstein's general relativity holds up in the most extreme gravitational environment that we can observe. Each of these science cases is currently just out of reach. GMT's instruments are designed to bring them within grasp. More powerful than JWST. So let's address the question that we posed in the title. I mean, we're 33 minutes in, or however this ends up, editors. We should answer the question. In what sense is the Giant Magellan Telescope more powerful than James Webb? Well, JWST has a primary mirror of 6.5 meters across. GMT's combined primary mirror spans 25.4 meters, giving it roughly 4 times the diameter at about 10 times the light collecting area. At overlapping wavelengths, in the near-infrared, GMT will achieve a diffraction-limited resolution of approximately 0.01 arcseconds compared to JWST's roughly 0.04 arcseconds. In simple terms, GMT can see finer detail and gather more photons from faint objects, at least in the wave bands where both telescopes operate. But raw numbers don't actually capture the whole picture. GMT has specific advantages that make it better suited for certain kinds of science. Its adaptive optics system, combined with specialized coronagraphs, will allow it to separate the light of exoplanets from the overwhelming glare of their host stars more effectively than JWST can manage. Its ultra-stable spectrographs, like GClef, can measure Doppler shifts within a precision that space telescopes simply are not designed to achieve. And perhaps most importantly, ground-based telescopes can be upgraded, maintained, and fitted with new instruments over decades of operation. JWST launched with its instrument suite fixed, and that's what it's always going to have. GMT is going to evolve as technology improves, potentially remaining at the cutting edge for 50 years or more. That said, JWST definitely does things that GMT cannot. Webb observes wavelengths out to 28 microns in the mid-infrared, far beyond what any ground-based telescope can achieve because Earth's atmosphere absorbs that light before it ever reaches the ground. Space also means no weather, no atmospheric turbulence to correct for, and no bloody daytime interrupting your observations. For certain science cases, particularly those involving very cold or very distant objects emitting primarily in the thermal infrared, JWST remains absolutely unmatched. The real power, though, actually comes from them both working together. JWST surveys wide fields, identifies interesting candidates, detects hints of atmospheres or unusual spectral features. GMT then zooms in with its superior resolution and spectroscopic precision to follow up in detail. The telescopes are not really competitors, we just put it that way in the title so you click on it. They're partners in a scientific enterprise that neither could accomplish alone, which is really cool. Money, politics, and the race to finish. But look, building a $2.5 billion telescope requires more than just brilliant engineering. It requires money, obviously, political will, and a coalition of partners willing to commit resources for decades. And on that front, GMT's story actually gets a bit complicated. The telescope is managed by the GMTO Corporation, a non-profit consortium currently comprising 16 founding institutions from 7 countries: the US, Chile, Australia, Brazil, Israel, South Korea, and Taiwan. International members include the Australian National University, the Korea Astronomy and Space Science Institute, and Taiwan's Academia Sincia Institute of Astronomy and Astrophysics. Each partner contributes funding in exchange for a share of observing time once the telescope becomes operational. So far, the consortium has invested about $1 billion, making it the largest private investment in a ground-based astronomical facility in history. But the total estimated cost is that $2.5 billion, which means there is still a way to go. And that's where things get politically interesting. You see, the project is currently about 40% done. Site preparation and foundations at Las Campanas are largely finished, with a massive telescope here already in place. The mount structure is under construction at Ingersoll Machine Tools in Rockford, Illinois, with components being manufactured across 36 US states before eventually shipping to Chile for assembly. First flight, with at least 4 of the primary 7 mirrors installed, is targeted for the early 2030s, while full scientific operations follow once all 7 segments are in place and the instrument suite is complete. In June 2025, the US National Science Foundation advanced GMT into its final design phase, a crucial bureaucratic milestone on the path toward potential federal construction funding. Normally, the NSF would fund this phase directly, but the GMTO consortium chose to cover the costs privately in order to maintain schedule pressure and demonstrate commitment. The hope is that this will position GMT favorably when the NSF eventually makes decisions about major facility investments in the coming years. Here's the thing. The United States has 2 competing extremely large telescope projects, GMT in Chile and the 30-meter telescope plans for Mauna Kea in Hawaii. The 2020 Decadal Survey recommended supporting both as part of a unified US extremely large telescope program, but federal budgets, they're not unlimited, despite how absolutely massive they are, and some observers worry that Congress may ultimately fund only one of them. If that happens, GMT and TMT would effectively be competing for survival despite serving complementary scientific roles. The Decadal Survey was blunt about the stakes. Without direct access to ELT-class facilities, American astronomers are going to fall behind. Adding to the pressure, Europe's extremely large telescope, a 39-meter behemoth under construction at Cerro Amazonas in Chile, is on track to achieve first light around late 2030, potentially years before GMT reaches full operation. That timeline means European astronomers could have access to ELT-class capabilities while American researchers are still waiting. A scenario that has generated real anxiety in US astronomical circles. Chile, for its part, benefits regardless of how the international funding politics shake out. Under agreements with the GMTO consortium, Chilean astronomers receive about 10% of GMT's observing time, a significant allocation that reflects the host nation's contribution of infrastructure, regulatory support, and access to some of the best skies on Earth. So, sometime in the early 2030s, if everything goes according to plan, the doors of a 65-meter enclosure will roll open on a mountaintop in the Chilean Atacama. 7 mirrors, each one cast in a spinning furnace beneath an Arizona football stadium and polished to a smoothness measured in billionths of a meter, will tilt toward the night sky. Maybe it will be the first instrument to detect signs of life on another world. Maybe it will unlock the physics of the early universe. Maybe it'll discover something nobody has imagined yet. Thank you for watching.